All right, today we're going to tackle a really neat algorithm called the symmetric difference. Now it might sound a little fancy, but trust me, it's all about solving one very simple, very common problem.
So picture this. You've got two lists of things. Could be anything, really. Guest lists for two different events, maybe product inventories from two different stores. The challenge is this. How do you find the items that are only on one list or the other, but completely ignore anything that's on both? How would you figure that out?
Well, it turns out there's a perfect name for this whole operation. It's called the symmetric difference, and it's often shown with this little delta symbol here. It is the perfect tool for finding exactly those unique, non-overlapping items we were just talking about.
Okay, so the definition is great and all, but let's be real. The best way to get a handle on an algorithm is to actually see it work. So let's walk through a super simple example with just two sets to make this really concrete.
Here we go. We've got set A with the numbers 1, 2, and 3, and we've got set B, which has 2, 3, and 4. Pretty straightforward, right? Let's see how this plays out.
So how do we find this symmetric difference? You might think we'd start by looking for what's different, but actually the trick is to start with what's the same. We need to find that common ground first, the elements that show up in both set A and set B.
And if you look at our sets, yeah, it's pretty easy to spot the overlap. The numbers 2 and 3 pop up in both lists. These common elements are the key, because they're the ones we're going to end up ignoring.
Okay, so once you've pinpointed that shared core, in this case 2 and 3, the rest is, honestly, a piece of cake. You just take them out of the picture entirely, everything else that's left over, that's your answer.
So after we toss out the common numbers 2 and 3, we're left with a 1 from the first set and a 4 from the second. And boom, that's it. The symmetric difference of A and B is the set containing just 1 and 4.
All right, that was pretty straightforward for just two sets, right? But what happens when we start throwing more into the mix? What if we add a third set or a fourth? Let's scale up the challenge and see how this logic holds up.
And this brings us to the single most important rule of the game, like the one thing you absolutely have to remember. Symmetric difference is what's called a binary operation. All that means is you can't compare 3 or more sets all at once. You have to work in pairs.
So let's put this rule to the test. Let's add a new set, set C, with the numbers 2 and 3. We have to work in pairs, so we start with the first two, A and B. We already figured that one out. It gives us 1, 4. Now, we take that result and we use it in our next operation against set C. So our new problem becomes finding the symmetric difference between 1, 4 and 2, 3. And, well, if you look at them, there's no overlap at all, so the result is just everything.
And just like that, we've got our answer. The final result for all three sets is 1, 2, 3, 4. See how that simple work in pairs rule made a more complicated problem totally manageable? It's pretty cool.
Okay, doing this by hand is awesome for really getting the concepts, but let's be honest, in the real world, we want computers to do the heavy lifting for us. And that brings us to the real goal here, turning this logic into a function that can do the work automatically.
So if we were going to build this function, what would our checklist be? Well, first, it has to be able to handle 2 or more lists, not just a fixed number. Second, obviously, it has to spit out the correct symmetric difference at the end. And last but not least, the final list it returns can't have any duplicates. It has to be a clean set of unique values.
All right, we've gone from a simple question all the way to the blueprint for a piece of code. So let's just take a second to boil it all down to the most important things you should walk away with.
Here's what you really need to lock in. First, at its core, symmetric difference is just about finding what's exclusive to each group. Simple as that. Second, and I'm going to say it again because it's that important, it's a binary operation. Always process just two sets at a time. And finally, remember that this simple, powerful logic is the perfect foundation for a function that can do this for you no matter how many lists you throw at it.
So I want to leave you with this thought. This isn't just some abstract thing from a math book, right? It's a real tool for sifting through data, for comparing and contrasting. You could use it to see what's changed between two versions of a document, or to figure out what files are different between two folders. Now that you get the logic, where do you think you could use it to find this signal in the noise?